Hello students, we have seen that trigonometric ratios are also related to circles. Basically, to understand trigonometry, we have to take help of circles. We talked about the unit circle, the circle with radius 1 in our previous video. Let me ask you, can we take a circle of greater or smaller than 1 unit? Yes, we can. It is because we know that trigonometry is all about shapes and not the sizes. So it doesn't really matter if we take a circle of size 1, 2 or 3 units and so on. This is why we can take any radius and the ratios are still going to be the same. We take 1 because it's easy to make calculations with it, isn't it? Yes. Multiplication and division becomes easy with 1. We discussed that sine theta is the height of this triangle for this reference angle. Well, this is because we have hypotenuse as 1, which is radius of this circle. And by substituting it in this ratio, we get AB as sine theta. Similarly, the base of this triangle is nothing but cos theta. The length of OB is cos theta. And tan is the distance on this tangent from this point where triangle meets the circle to this point where this tangent cuts the x-axis. So we now know that what is the logic behind using tan. But what about logic of these inverse ratios of these three? How to visualize them on the circle? If you observe that tan and cotan, they both are on the tangent, while sec and cosec are located on the secant of this circle. Observe that tan is the distance between point P and point A, which is on the x-axis. Yes, where tangent cuts x-axis, while cot is the distance between point Q and A, which is on y-axis. That is, where tangent cuts y-axis. Now again, sec theta is the distance between this point and O on the secant, which is the x-axis itself. And cosec theta is the distance between points Q and O but on the y-axis, that is on the y-secant. So if you see all these tans, sines and secants which do not have co before their names, they are cutting the x-axis, while all the ratios with cos in their names are cutting the y-axis. Tan cuts the x-axis, while sec is itself on x-axis, while sine also cuts x-axis. But cot and cosec cut the y-axis. In fact, even cos cuts the y-axis. See, if we draw a line just parallel to this cos here, since it is parallel, this distance is same. It's not changing. But what we have done is just shifted cos from here to upwards. And now if you see this, because it cuts the y-axis, yes, it is perpendicular from point A to the y-axis, it is named so. Now just think for a second about an angle formed between x-axis and y-axis. Well, this is just for simplicity and remembering. So you can see here that this angle is 90. Now we know that in maths, if two angles sum up to 90, then they are complementary angles. And since x and y have a 90 degree between them, trigonometric ratios which cut x and y are also complementary to each other. The cot, after all, is complementary to tan, which is why we have this co for complementary here in front of the tan. Similarly, cosine is complementary to sine and cosecant is complementary to secant. Well, this is just to make things easy and quick for you to remember. Why they are complementary, we will learn in some other video. But for now, we know the logic behind the names of these trigonometric ratios. Okay, so we know how are these ratios associated with triangles and circles for now. Let me tell you one more interesting fact about these ratios. Trigonometric ratios are also known as trigonometric functions. So what exactly is this function? A function in maths relates an input to an output. Usually there are three main parts: the input, the relationship, and the output. Let's look at it like this. Say the function is like this, a machine. Here is the input and here is the output. In this machine, what matters is what is inside this part. That is, how it is processed. Inputs and outputs may change with values, so they are not that important. But the operation on values is always the same, and which is the important part. So what matters is what happens inside this part of the machine. That is what operates on these values. Say for example, we have a multiplication with 2 in this operation. So when the input is 2, the output will be 4. When I give 3 as input, the output will be 6, and so on. Some other examples are like squaring, which is a function, x cube plus 1, which is also a function, or an operation that can be done on different values. Trigonometric ratios like sine, cosine, and tangents are also functions. And there are a lot more. The most common name for any function is f. Yes, it is symbol as well. But we can have other names like g or even say p, q or s. But let's use f to represent any function here. We say f of x equals x squared. So we represent it like this. F x displays the function f, which is squaring, and x, which is the value of input that is being entered. So fx is x square, indicates that function f takes x as an input and squares it and gives some value as an output. If an input of 4 is given, it becomes an output of 16 after squaring. And this is what f does here. In fact, we can write it as f into bracket 4 is equal to 16. So what this function does is that it squares any input that is given to it and gives squared value as an output. So we usually see what a function does to an input. It processes it and gives us an output. Well, don't get too concerned about this x. It is just to show us where the input goes and what happens to it. It could be any value, anything. What is important is what happens to it. That is, what does this function box do to an input? So a formal definition of function can be a function relates each element of a set with exactly one element of another set. Coming back to our trigonometric ratios, they are also called as trigonometric functions. Sine, cosine, tangent are three important trigonometric functions and are abbreviated as sine, cos, and tan. We also have three other inverse ratios of these three ratios. So now what we know is all about ratios, which are nothing but some sort of functions of some angles. And to understand trigonometry, we also need to understand these angles. What we always do is we use the information that we know to understand what we don't know, isn't it? Yes. So here also we will use these ratios of the side, that is something we know, to understand more about the angles, which we don't know. Basically, what I want you to think about is, what if I change this reference angle to less or more? Do we see any change in the values of these ratios or functions? Do they increase or decrease? And if yes, then how? We will see you in the next video.